Okay, Assalamualaikum and good morning. So we'll continue with our lectures. So let me get to the notes. So I think we have done this. So let me just see precisely where we left. Okay. So I believe we have done the Lorentz transformation with the Lorentz identity. So, and then we are looking at a particular case of the Lorentz transformations. So, one that we did yesterday was to look at this Lorentz transformation that preserves the time coordinate, and that amounts to simply just your rotations. Okay, so in other words, there is no what you call the only changes that you see will be the spatial coordinates due to the rotation of the inertial frames. Okay, so an example would be something like this. So again, one has to rely to something that you have seen before in probably in mathematical methods. Here is the case of a rotation matrix that keeps the x coordinates fixed as well as the time coordinates being fixed. So what actually happened in this particular case, your 4x4 matrices that represent your Lorentz transformation will have your 1 1 position to be just simply equals to 1, and then the rest in the row and column should be 0, as well as the 1 in the fourth column and the fourth for matrix entry. So it will be just 1 there and then 0 elsewhere on the fourth column and fourth row. Okay, so this is essentially some forms that I expect you to know precisely. I might ask you what would be the Lorentz transformation that keeps y fixed and z fixed and other coordinates might be transformed. So you are able to actually identify what the matrix looks like. Okay, so here is a rotation matrix that keeps x fixed. That means your rotation axis is actually along the x-axis. So in other words, in this particular case, only your y coordinates and z coordinates will change according to this rotation matrix element. Okay. So now what we want to do next is perhaps a new kind of transformation that probably is different from the ones that you have seen in Galilei transformations. Okay, so this will be a Lorentz transformation that keeps your y and z fixed, but everything else is actually changing. So in other words, your x will change and your time coordinate will change. Okay, so if you think about again how the matrix should look like, so there will be a 1 on the 2 element. Remember the y coordinates is considered as the second coordinate, x2, okay, and the z coordinate is x3. So you have 1 0 0 1 in the middle, this particular block. Okay, but then and also of course anything on the second row and the second column will be 0, okay, apart from the diagonal case, and also the third row and the third column will be 0 apart from the diagonal. Okay, so one is left with these 4 different elements which we have to find out what are their properties. Okay, So again, what we need to do is to impose your Lorentz condition. Okay, remember the Lorentz condition that we had earlier from the identity. Let me just recall that. Yeah, I think it's here. Okay, so one will need to impose this condition, particularly involving with those elements which are not zero here. Okay, so one would be interested, for example, the Lorentz condition when you have eta for 4, and eta for 4 is -1, of course, and then the Lorentz condition says this: you have L mu dash 4 eta mu dash L mu dash 4, okay, where mu dash and nu dash are being summed. Okay, but remember that now essentially your mu dash and eta mu dash and nu dash is going to be diagonal, so they have to be the same. Okay, the mu dash and nu dash has to be the same in order to become non-zero, otherwise it's zero. And then the other thing that we have seen is anything with if you look at this, anything which has the index different from 1 or 4 will be 0. So the ones that's going to be left is going to be L1-4, and then here you have eta 1-1 dash, okay, and then L1-4, which gives you L1-4 squared. Okay, multiply these two together, and then you do the other sums. 2 dash, well, you know that L2 dash is going to be 0, okay, that will be this one, okay, and then L3 dash is also going to be 0, and the next thing that we have is going to be L4 dash, okay, L4 dash 4 eta 4 dash, and then you have to have 4 dash as well here, and then L4 dash 4, okay. So eta 4 dash 4 dash is going to be -1, so that gives a minus sign here, and you're left with L4 dash 4 multiplied twice, and you get that to be squared there. Okay, and then you have to do the same for the other components of the Minkowski metric. Okay, your eta, and remember one only needs to check with the case of the index being 4 or 1. So eta for 1 and eta 1 4, which is known to be 0, and then you find out what is the equation on the other side, and that gives you this. Again, with the same technique as before, you have the sum, and then the sum for eta for 1 and eta 1 4 is actually the same equation. Okay, so you have that, another equation to consider, and then eta 1 1 is actually equals to 1, and again you have something similar to that. Okay, you have L mu dash 1 eta mu dash nu dash L mu dash 1, and then you sum it over all possible values of the indices. Where are we? And then you'll get this particular equation out. Okay, L1-1 square minus L4-1 square will be equals to 1. So let's look at, let's number this equation by 1 to 3 here. Okay, remember the 2 is the same equation. Okay, 1 and 3 gives you a difference between 2 squares equals to -1 or +1 here, and then you can rearrange it in this particular form. Okay, so you get L4-4 squared. This is coming from here, and then you bring this -1 to the other side, so you get L4-4 squared equals to 1 plus L1-4 squared. Now you can see that this is a sum of a positive number, 1 and this square. Okay, so in other words, L4-4 squared has to be greater than or equals to 1. Okay, and similarly, you rearrange the third equation. Okay, in this particular case, you bring this on the other side, and then again you get the fact that L1-1 squared is a sum of positive integers, positive numbers, not integers, positive numbers greater than or equals, so which gives you a greater than or equals to 1 number. Okay. Now at this stage, probably this will be a bit kind of a mysterious move, but one needs to compare this with the hyperbolic function, for example, of the hyperbolic cos x, which is given as, in terms of exponential, is just ex plus e minus x divided by 2. And both ex and e minus x are always positive. So in other words, you have cos x is always greater than or equals to 1. Okay, so you can actually show that if you want to. Okay, but suffice that we accept this identity, cos x is greater than or equals to 1. Then one could essentially apply this to these two inequalities that we have seen above. So one assume that there are two values of this x over here, one corresponding to the L4-4, which we write as cos alpha, and then one corresponding to L1-1, sorry, which we write as cos beta. Okay, so one needs to look at what would be the other, so you identify this as cos alpha and cos beta. One has to find out what would be the other matrix element of the Lorentz matrix. Well, one of the things that we have seen earlier was to have this equation equals to 1. Okay, this is from equation 3. Okay, from here. Then with this, what's going to happen? I've already identified L1-1 to be cos beta, so I can insert this inside this particular equation. Okay, and that tells us, okay, by just rearranging the equation, then you'll find that this is equals to L1-1 squared minus 1 square root. And when you put this on the, you substitute the L1-1 to be cos beta, so you get cos squared beta minus 1, taking the square root, and you use the hyperbolic identity, which is cos squared minus hyperbolic sine squared equals to 1, and that gives you a sine, hyperbolic sine beta, or shine beta, I would like to call it that way, easier. So similarly, again, for the other case, one would have L1-4 to be a hyperbolic sine alpha. Okay. Now, what about the other things that we had earlier, which is equation 2? Okay. Well, now we have given labels to this, all these matrix elements. Okay, L4-1 dash, L1-4. So they are given in terms of alpha and beta. So the second equation, which we have not used yet, will give you this equation here, which is cos beta sine alpha minus sine beta cos alpha equals to 0. But this, if you remember, there is a what you call addition formula for this hyperbolic trigonometric functions. This actually gives you a sine alpha minus beta. okay? And sine alpha minus beta must be equal to 0. That tells us alpha must be equal to beta. So finally, we get it in this particular form, which is quite nice, okay? So you get cos alpha, sine alpha, and then over here you have the identity block here, and then sine alpha, cos alpha. Now, it reminds you a little bit of the rotation matrix. Remember, the rotation matrix earlier is in terms of trigonometric function rather than hyperbolic. So you have cos theta, sine theta minus sine theta, cos theta. Here it's almost the same thing, but it's in terms of a hyperbolic function. Okay, but hyperbolic function and trigonometric functions are related in some way. Okay, if you use the complex number, okay, then you can show that your cos alpha is actually cos I alpha, and sine alpha is minus I sine I alpha. So now it really looks like the case of a rotation matrix. Right, where are we? So the only difference now is probably, no, there are two differences, of course. One is the fact that your angle seems to be imaginary. And then usually when you have your rotation is, this will be cos, this will be sine, and then this will be minus sine. So that's the only difference. Here, both are actually having a minus sign, okay? So, but okay, let's see what this corresponds to if we consider properly how is the relationship with the case of what you call moving frames, okay? Now, again, another magical step, something out of the blue, but because we already know the answer beforehand, you can set your hyperbolic tangent of alpha, for example, equals to minus v over c. Remember your hyperbolic function or even trigonometric function. The argument has always to be what you call a dimensionless quantity, because you have power series in these functions. Okay, so a natural thing to have is to have a dimensionless quantity given out from your velocity of the frame divided by the velocity of light. Okay, so if we do that, so this is again out of the blue kind of step. If you do that, what is your cos alpha and sine alpha? Well, your cos alpha is given by 1 over square root 1 minus hyperbolic tangent squared alpha, and that corresponds to this factor here. And similarly, for hyperbolic sine alpha, you will get this particular factor here. Okay, and this one is quite nice because what you see you get back to the Lorentz transformation that you probably have learned in modern physics. So here is a transformation of your x coordinate here, x1 dash as written as x dash, and then x1 is your x, x4 is, remember, has been written in terms of time coordinate here. So this you can actually rewrite this as v over c times ct, okay, and that gives you a vt there, okay, and you just plug in your cos alpha and sine alpha. Of course, the v over c is actually already coming from the sine alpha, okay. So in other words, we get the Lorentz transformation that we have seen in modern physics for the case of the x coordinates. Similarly, for your x4 dash coordinate, which is actually ct dash, you'll get this particular relationship. Again, this is something you have also seen together with this transformation of your x coordinate. There will be a transformation of your t coordinates. And this is precisely the boost transformation. Probably I mentioned the boost transformation earlier. So this is actually you boost your inertial frame with velocity v along x direction. So once you have that, it will also implies there will be changes in the time coordinate. Okay, so your boost transformation is like a rotation. Okay, as I mentioned earlier, is in a way is a rotation of an imaginary angle, but that is precisely how one should think of it in a way. Okay, it's you have your now that you have your vector of position is given by the three spatial coordinates and time coordinate. That gives you 4. Okay, and then this would be a rotation that sort of mixed up between your x coordinate and your time coordinate. Okay, so that's a nice what you call generalization of a rotation in some sense. And normally there is some notation, standard notation that people use. These factors that you see, always comes about inside your boost transformation. This is called a relativistic factor, 1 over square root 1 minus v squared on c squared. So this is written as gamma. And also the thing, this ratio v over c is written as beta. Okay. So generally, one can think of your boost transformation is written as gamma 0 0 minus gamma beta here, and then gamma, and then your y and z coordinates are not changed. So this is a boost along x direction, making your inertial frame having a constant velocity in the x direction. Now I can ask you without doing any proof, okay, give me a boost in z direction. Then one ought to be able to see how to write that the matrix of boost transformation in z direction. Because you can see how the matrix elements are supposed to behave. Okay, so I think so. This will be the end of this particular lecture notes. Okay, maybe I'll return to the class to see if there are any questions from the audience. Anything that you want to ask at this stage? No? Yes or no? Not yet. Okay. So okay, take your time to digest. I believe the notes has already uploaded for this lecture 4. So now, if you like, it's too early to take a break now. So okay, maybe I'll continue. So the next lecture is to see the consequence of this Lorentz transformation, particularly the ones that we would like to analyze a little bit more is the boost transformation, because rotations, you have seen this before. They are part of the Lorentz transformation, but no, already used to rotations in classical mechanics. So the one that we are being interested more will be the Lorentz boost transformation. And for simplicity, we just continue with the case of the Lorentz boost transformation along the x direction. So this is the boost transformation that we have seen earlier. Okay, for the case of the time, I already rearrange it so that I get just your t dash over here. Okay, and essentially sometimes, okay, this is like your x, y, z, t is your O frame. Okay. This might be considered as stationary. Then you have x dash, y dash, z dash, t dash. This will be your O dash frame, and O dash frame will be traveling with respect to the O frame with velocity v. Okay. Now, so this is how you relate between the O and O dash frame. So here's the O coordinates, and then this is the O dash coordinates. Now, one should be able to also, once you have this equation, for example, then one should be make the what you call get the inverse transformation readily from this equation. Okay, because if O sees O dash frame what you call moving with velocity v, O dash will think of itself in its own frame. O dash will think itself is not moving, but O will be moving. Then you know that this will move in the opposite direction, which is going to be minus v. Okay, so one simply replace your v with the what you call with the velocity of the O frame with respect to the O dash frame, and basically you get plus v instead of minus v here, and the same thing over here. So now is the O dash frame looking at the O frame having to make these particular changes. Okay. So that's the first thing that you should be able to know almost automatically. Okay. The other thing is probably we want to draw some axes. Okay, so this is going back to space-time diagram. So a revisit of the thing. So earlier we had this kind of thing earlier. Okay, so this is O frame, for example. So it has the time axis this way, and then you'll find that O dash is moving with some velocity. So the whirl line of O dash will happen to be what you call making a kind of slope, showing that it's actually moving with respect to O. Okay. So what is that axis over there? It's essentially if you really think what is, for example, when you write, okay, let me just draw this here. This is x, this is t. What is precisely this axis? This axis is essentially x equals 0. And what is precisely this axis? This is precisely t equals 0. Okay? So in other words, the thing that we had earlier that makes a particular slope in this way, that shows that O dash is actually moving, is you think of it as, okay, according to O, O starts with 0 0 in its frame. So this is actually essentially what you call the partial coordinates of O dash according to O dash himself is just the 0 is x dash equals 0 coordinate. Okay. So in other words, the x dash equals 0 coordinate will actually label, will actually gives you the t dash axis. So we have that t dash axis. Okay, so that's settle one, and you can actually get what that axis is supposed to be. This is coming from this equation before. So you get essentially, let me see, I need x dash to be, no, it's not the other one. I need x dash to be equal to 0 here. Okay, that means x is going to be equal to vt. Okay, so you use this one. Okay, so x dash equals 0, so essentially I need x minus vt equals 0, or x equals to vt. Or in other words, I can rewrite this x equals to v over c, which is a beta here, times ct. Okay, and if you can see earlier when we did this identification of v over c with your hyperbolic tangent. Okay, and this hyperbolic tangent is always less than 1. Remember, your light travels with x equals ct here, okay, and if c equals to 1, so it's just your 45 degrees what you call slope angle there. Okay, so that is your time axis for your O dash. Now we have to do also the other axis, should be the x dash axis, and the x dash axis should be t dash equals 0. Okay, so if you look at that, so I will have t dash equals 0 there. That means t minus vx on c squared will have to be equal to 0, or I can rewrite this as ct equals to v over cx. Okay, and you can actually draw that line, and it actually gives you this particular x dash axis. And you can see that, okay, something a little bit strange here. You know that your time axis and x axis in the case of the O frame is actually orthogonal, but here it doesn't seem to be orthogonal, but it's just the perspective of O looking at this O dash frame. To O dash itself, this is actually orthogonal. Okay, so these are some of the funny things that comes about with this space-time diagram. Okay, and the other thing that one can actually see again by looking at the equation, the angle that it makes between this t dash axis with this t axis, and then the x dash axis with the x axis is the same angle. Okay, so of course this again is in the perspective of the O frame. Okay, so this is actually a moving frame with some slanted line kind of axis. Okay, now given this new set of axes of the O dash frame, you might want to consider, let's say, okay, consider an event P. How can you actually assign coordinates of this event P? Well, let's do it for the ordinary case. So what do? You draw a horizontal line with the t-axis, and that gives you the time coordinate according to O, right? And then you do a vertical line axis, a vertical line projection over here, and then that gives you the x coordinate of that event P. Okay. Now, think of it, what actually has been done here is that this horizontal line is a line that is parallel to the x-axis. And this vertical line is just a line which is parallel to the t-axis. So guess what's going to happen when you do it in the O dash frame? Okay, what is needed in this particular case, if you want the time coordinates, I will draw a line parallel to this axis to get the time coordinate. Okay, so this is parallel. Okay, and then what about the x coordinate? So I will draw a line parallel to this axis. Okay, so I have that. Okay, so that will actually now give you coordinatize this P according to the O dash frame. Okay, so once you have this space-time diagram, you can actually coordinatize any events quite easily. Okay, so that is how you coordinatize things. The only problem is that if you try to draw, one of the problems you'll see later on when you try to draw it, how this what you call transformation actually changes the scale of the axis itself. Okay? So one of the problems is to understand this properly. So how can you define scales on the various different inertial frames? Well, we have seen earlier, one thing that doesn't change from one frame to the other is always your four-dimensional interval square. So we make use of this to actually set up a scale for each reference frames. So let's do this for the case of a simple case before we do thinking in terms of the full dimensional three-dimensional space and time and one-dimensional time, sorry. So we restrict ourselves to one-dimensional space and one-dimensional time. Okay, so then you can see what kind of equation comes out from this thing. Well, remember dx squared is what? It's dx squared plus dy squared plus dz squared minus c squared dt squared. So if it's one space and one time, sorry, one space and one time, I would only have this. So the curve that sort of set the scales will be of this particular form, x squared minus c squared dt squared. Okay, so this value should not change in any of the frames. Okay, so if you go to the O dash frame, this would also be of the same value. The individual coordinates might change, okay, but this value of your x and t for you have to remember this actually refers to a particular event. Okay, your x and t for a particular event here will have that value, and that value will also be the same for the event in for the coordinate of this event according to the O dash frame. Okay, so that essentially is an equation of a hyperbola. Okay, so if you you take the square root of this, then you find that your time coordinates related to your x coordinate by this particular this is asymptote. Okay, this is the quadratic equation. Okay, but for the asymptote, you sort of equate this to say x squared minus c squared t squared equals to 0. So that will give you the asymptote of ct equals to plus or minus x. Okay, so it's equation of hyperbola in the O frame and also in the O dash frame. So that doesn't change. Excuse me. So if you draw a hyperbola in the space-time diagram, you'll be able to find out okay, what kind of scaling that one should put on this time axis and what kind of scaling you put on this x-axis. So you'll see that, okay, since the hyperbola, this hyperbola, this hyperbola, this hyperbola, they look the same in both frames. Okay, so if you look at where the hyperbola cuts the time axis, that will set up, say, okay, maybe this is x squared minus c squared t squared equals to 1. So that will set up this coordinate 1 on the time axis. Okay, and then I would have something the other way also that will give you a different hyperbola. Let me just think about it. So that is going to be c squared t squared minus x squared equals to 1. Okay, and that gives you a 1 on this what you call axis, and the other one is actually giving you this one on the x-axis. Okay. I have to check with this one, okay, but no, more or less, because they belong to the different hyperbolas, okay. And then what about the x dash axis and the t dash axis? Remember that this curve is now the same in all frames, so this will also set up the scales on your t dash axis. So you see where it cuts the t dash axis, that will give you the the unit. For example, this is this will now be that. Sorry. Let me write this properly. I have to think properly. C squared t dash squared equals to 1. Okay, so that will give you this particular what you call scale along the t dash axis. And similarly, there should be something similar. I'm not sure about this equation, but no, you have another equation that tells you about this parabola cutting this x dash axis at that point. Let me just think carefully whether this is correct or not. So I'll be getting I think yeah, I think it should be that. Then I'll confirm in the next lecture, I suppose. So this will actually give you the unit scale for the x dash axis. Okay. So and you can see that no, this length and this length is not the same. This length and this length is not the same. Okay. But according to t dash, this is actually a unit length. This is also a unit length. According to O, this will be the O's unit length, and this will be O unit length in the O frame. Okay. So that is how one has to be careful about when you draw the space-time diagrams. You have to remember that the scales are actually different on the axis of the different frames. Okay. Okay, let's look at one particular case of what you have seen, and hopefully you have seen this in modern physics at least. One of the things that one can actually talk about in a space-time diagram is about simultaneity. Two events are considered simultaneous. For example, here is one event here. This is another event here. So in other words, we have something like this. This is t-axis, this is x-axis. Two events are going to be the same, two simultaneous if they have the same coordinate. So this is, say this is x1, this is x2. So your t1 and t2 is the same. Okay? But now what I can start to do is, if it's the same in the O frame, can we find out whether they are the same inside your O dash frame? Well, we can look at this difference between the two coordinates of T2 dash and T1 dash. Okay, so you will look at, okay, how do you find the time coordinates for T dash? So you have that, right? So you plug in that formula to find T1 dash and T2 dash. And okay, I get this gamma times, no, this is coming from the T2 dash, sorry, and this is coming from the T1 dash, but T2 and T1 is going to be the same, so that will cancel off, but X1 and X2 is different. Okay, so this will not cancel. So in other words, you'll find that, okay, because these are two different values, you find that your T2 dash minus T1 dash is not going to be equal to 0. The only time they coincide is when you consider they are actually the same event, okay, which is, in this particular case, we define it's not. So in other words, what happens is this strange phenomena that you get in special relativity is that your idea of simultaneity is not really preserved. Okay, so it always gives you, if you really want to refer to the invariant, for example, I have that equals to that. Now if this is actually equals 0, you still have if you look at what delta t dash squared is going to be, this is not going to be 0 because you have delta x squared minus, delta x dash squared minus delta x squared. Okay, so there you see that, okay, we have this sort of well, it's not really strange, but the fact that one frame is actually moving to another doesn't actually tells you that your what you see in one particular frame is going to be preserved in the other frame. So I can't say anything more simpler than that. Okay, so let us see what actually happens here in a space-time diagram. So this is the same picture that I drawn earlier, but now we have the t dash axis and the x dash axis. So these are the two events just now. Okay, so your x1 is here and x2 is somewhere here. Okay, so they are occurring at different places in the O frame, but they are at the same time coordinate. Okay, so that is simultaneous for the O frame. Now, if I want to see what is this coordinate and this coordinate according to O dash frame, remember what we need to do? We need to draw a parallel line to this axis. Okay, so this gives you the coordinate of event 2. Okay, and this gives you the coordinate of event 1. Okay, so you see that, okay, it doesn't quite coincide like what you have over in the O frame. Now the picture is also the same when you see a simultaneous event in O dash frame. So here is two event which is simultaneous in the O dash frame, because how do you see that it's simultaneous here? So you draw a parallel line to this axis. So I get that. So A and B here is simultaneous in O dash, okay, because it projects to this time, okay. But when you project it, so A and B is simultaneous in O dash, but if you project it along the O frame, so remember you draw again a parallel axis according to this, and then parallel axis according to this. Sorry, parallel lines, okay, parallel to this axis, okay. So you get your time coordinate for A is that, time coordinate for B is actually that. So even though this is simultaneous now in the O dash frame, it's no longer simultaneous in the O frame. Okay, so you get all this nice diagrammatic description of things that happen in special relativity. Okay, maybe I should take a break at this stage before we go to the next case. Shall we? Okay, so okay, stay around 5 minutes. Okay. Shall we restart? Anyone? All right. So okay. So we have seen one particular sort of in the classical sense. Well, in the classical mechanic, classical. Hello. Yes. Okay. In the classical sense, that we do not expect this idea of simultaneous events to be changing with respect to moving frames. Okay. So here's another thing that one actually see also does not quite preserve when you change to a different reference frame. So you consider, for example, the phenomena of a length contraction. Probably you have seen it in modern physics. Now, let's try to think this in terms of a proper context of a space-time diagram. So when you define the length of a rod in a particular frame, it's usually considered you're trying to measure the length at some simultaneous time. Okay, so over here, this is the endpoint of one endpoint of the rod given by x1. Okay, and at the same time, okay, in order for you to actually find the length of the rod, okay, at the same time you also identify the coordinate of the endpoint, the other endpoint of the rod. Okay, so then you do so you consider these two events, simultaneous event, and then you take the difference between the coordinates, and then you get your length of the rod. Okay, but if you consider what actually happens inside the O dash frame, it doesn't quite give you a simultaneous event as we have seen earlier. So you get this T2 dash. Somebody is trying to say something. Is that a question? Let me mute that. Okay. All right. So in other words, how we define the length is through measuring the two endpoints simultaneously. Okay. So the same way you measure the length of the rod in the O dash frame. How do you do that? Is to measure the endpoints simultaneously inside the O dash frame. Okay. So let's try to think of how to do that. Okay. So in other words, over there. Okay. So here is the L given by measured by O, but that gives you a non-simultaneous event inside your O dash frame. Well, if according to O dash, if we want to make this as a length, then T2 dash and T1 dash has to be equal. So then he will get the length inside the O dash frame. So let's do this momentarily so that you can actually sort of, how should I say, we momentarily try to compare the length measured by O and O dash. Okay, even though that in one of the frames it's not going to be simultaneous. So I'm going to set this T2 dash and T1 dash to be equal just to make the comparison. So when you do that, so I will get L equals to gamma times x2 dash minus x1 dash, okay, which tells us, okay, this will be the that is measured by O dash. Okay, remember there is actually this time coordinate, but we set it so that we can compare the length measured by O dash with the length measured by O. Okay, so how is these two lengths are related? It's going to be related by this equation, which is L equals to gamma, and this we call it L dash. Okay, L equals to gamma L dash, or L dash is given by L divided by gamma. Remember, gamma is what? It's 1 on square root 1 minus v squared on c squared. So L on gamma is square root of 1 minus v squared on c squared times L. And this, for ordinary velocities, which is less than speed of light, this is less than 1. So in other words, what O sees, how O dash is measuring is, so the measuring rod of O dash, okay, is going to be contracting. Okay, so in other words, L dash as measured by O dash is seen to be smaller than L as measured by O. And hence, this is the kind of the result that we have seen in modern physics, perhaps, and it's called the Lorentz Fitzgerald contraction, which says that the length of a moving rod actually contracts. Okay? Now, it would be good for us to be able to see this in the context of a space-time diagram. Okay, so here is the context of space-time diagram saying a simultaneous event. So this x1 dash and x2 dash are simultaneous here. Okay, and this is essentially the length of this rod according to O dash. But how does what you call O sees what's happening? And again, in the context of O, it always measures the length according to drawing a vertical line parallel to this axis. Okay, and it says okay, that length of the rod is actually given by this L here. Okay, but how to compare these two things together when they are not really simultaneous in both frames? So, well, we have the one thing that we know that is that the hyperbola that we have seen before is going to be invariant. So one can start to draw this hyperbola going through all these events if you want. Okay, and then okay, here is the same L dash that is seen by O dash over here. Okay, drawn in this way because this is actually S1 dash here and S2 dash here projected on the S dash plane. So this is the same L dash if you want. But now I want to compare with this thing, so I need to project this thing down to the x-axis over here, and that is going to be now you don't project by using the vertical line, but you use the invariant hyperbola. Okay, so the invariant hyperbola sort of take this point down to this point and take this point down to this point, and that will be the L dash. Okay, and that L dash will now be compared with this L, and again you can actually see that this L dash is supposed to be shorter than this L. Okay, so okay, that's the length contraction. I think this is just the explanation what I have mentioned just now. Oh yeah, so here is another thing. I'm thinking of the rod just now just like a one-dimensional thing, but you think if you see a rod in real space, there will be the thickness and the height. So one can actually ask what actually happens with those dimensions. Well, remember that the one that's been changing is only the x and t. Okay, because you have a boost in the x direction, so you simultaneously change the x coordinates and your t coordinates, but it will not change your y and z. So this, according to the Lorentz boost in x direction, will not change your y coordinates and z coordinates. Okay, remember the kind of matrix that we're supposed to have. You have something here and then 1, 0, 0, 1, something here, something here, something here. Okay, so your y and z doesn't change under the when you go to the different frame. So there will be no shrinkage or no contraction in the perpendicular dimensions to the x-axis. However, because it's already contracting in the x direction, that means your volume, however, will change. Okay, even though the other dimensions doesn't change, but the volume actually changed by the same factor that you have seen before. Excuse me. Okay, sorry about that. Just letting the cat out. Right. So that is your length contraction. The other thing that one probably has learned in modern physics is that your time gets dilated, or another common way to say is moving clocks run slower. Sorry. So again, what one can do is to think of how clocks ticks in two different frames. So here I'm drawing a line so that tells us, okay, this will be a time interval in O, some delta t here, and that will give you a different, if I draw it in the other way, okay, I mean, if I really want to compare this, I have to draw this line, but I can also look at this particular line, which is parallel to this axis, and that will tell us about the C2, the T2 dash and T1 dash, okay? So now if one looks at, okay, this is the time interval that one has over here, and we now use the Lorentz transformation on the time coordinate, so we actually have that, okay? And let's assume that your x dash is the same, so this cancels off, okay? This is the same problem as the length contraction in some sense, so you're letting your spatial coordinates to not change at this stage. So then what one has in this particular case is that your time interval in your dash frame is related to the time interval in the undashed frame by this amount, okay? And you can actually see what happens over here. Your gamma is 1 over square root here. So this quantity is going to be bigger than T2 dash and T1 dash. So if you really think what's happening over here, the time interval here is actually more than the time interval here. And because there's more time interval here, the clock ticks faster here. And what it says that in this particular case, the clocks on the O dash frame ticks slower, so that you find that this difference actually is less than this interval, the value of this interval. So this events, this sort of interval says that, okay, the moving clocks in O dash frame sort of moves slower than the clocks in the O frame, okay? It's a bit confusing, but one has to think in terms of the ticking of a clock, okay? And that phenomenon is called time dilation, okay? Now, one could ask this, this is a famous problem in relativity, and one could ask, okay, if O sees O dash moving and then O dash clock is going to move slower, then O dash will also see the same about O, okay? Because O dash will see O is actually moving, and then the clocks of O, which is moving, is also slower. So in other words, the effect is actually symmetrical in both conditions. But then who is right, who is wrong? You might want to ask. Any answer? Whose clock is actually really moving slower or moving faster? Let me see. Have you come across time dilation inside modern physics? Okay, so now who is right and who is wrong? Whose clock is actually moving slower? No one is right, no one is wrong. Right, both are right because they are actually comparing what you call comparing things in different frames, and of course they will never quite coincide unless you bring the clocks together. Okay, then you can actually uh, tell precisely who's actually moving in that particular case. So that amounts to twin paradox. So the twin paradox is essentially saying this kind of problem. You have two twins, okay? One is set to stay on the Earth, okay? And then the other actually stays on a spaceship, went for a space journey, okay? So both sees the other clock, okay, moving slower. The one on the Earth will see the one on the spaceship, the clock is moving slower, and the one on the spaceship saw the clock on the Earth moving slower. Okay, but in order to make comparison, one has to bring the clocks together in the same frame. So, and in order to do that, the twin on the rocket, okay, usually you don't bring the Earth to the rocket, so you bring the rocket back to Earth, okay, and compare the two clocks. So what happens in this particular case, let me just here's the diagram from one of the books by Takeuchi. Okay, so what actually happens when the spaceship is about to return to the Earth? Usually, what happens is it will slows down and then momentarily at rest and then returns back to Earth. Okay, so what happens in this particular stages, the rocket experience acceleration or this initially deceleration and acceleration. So once the rocket decelerates and accelerates back to Earth, okay, then you'll find that these are no longer an inertial frame. Okay. So when it's no longer inertial frame, the symmetry between the two what you call perspectives, so to speak, okay, breaks down, and then also the person inside the rocket says, okay, it's my problem because I'm no longer in an inertial frame. And then I can actually see that, okay, the clock that actually moves slower is mine. Okay, and then when he returns back to Earth, he finds that the twin on the Earth has already aged quite a lot, whereas he himself, being having the clock moving slower, will not age that much. Now you might find that this is a bit odd, but this has been done experimentally. Okay, so I would like to change to this thing, so you might want to read this for yourself. There is an experiment done by Hafel. What's happening? Oh yeah. There is this experiment done by Hafel and Keating. Okay. So they did an experiment bringing atomic clocks. So atomic clocks are very accurate. Okay. So one is flown eastward and one is flown westward. Okay. And then they can compare this with the atomic clocks on the Earth, and they saw some difference. They actually do the results over here. Okay. So do you see the one because the Earth is actually rotating eastward, right? Oh, sorry, westward. Sorry, westward. So there will be differences with respect to the velocity of the rocket, or in this case I'm not sure what is. It's an airline. see, yeah, commercial airline. Okay, so there will be a slight difference between the airline moving eastward and moving westward. So you see this kind of differences. Oops, I can't annotate on the web page. Okay, you can see this kind of differences. And the thing that sort of complicates why is this not taught inside special relativity, really, because there is not a complication that comes from the gravitational forces. And this is usually taught in general relativity, so there will be changes also with respect to this gravitational field. Okay, but you can see some difference. Okay, some difference over here in nanoseconds. Okay, so it has been done experimentally, and what is actually the difference taken into account of both what you call theory of special relativity and general relativity, and it's precisely the ones being what we call taught by relativity in the ordinary circumstances. Okay, so I'm not going to go into that, but you can have a read on that experiment if you want to. Maybe I'll put this as one of the there will be a student-centered learning module, so maybe some of you can actually study this particular paper. Okay, right, so start to move on. The other thing that we have learned in Galilean relativity is the idea of addition of velocities in a moving frame. You consider, for example, if you have so you have two frames here, so O here and O dash. O dash is moving with velocity v, and then inside your O dash frame there is another object moving with velocity u, for example. Then what O observes is that this object is moving with a faster speed, which is given by the ordinary addition of velocities. Okay, so we would like to see what is the kind of addition of velocities that you can actually get when you have special relativity. So in this particular case, what one does is to look at the formula of the speed itself is given by the change in x divided by change in t, and respectively in the O dash frame is given by change in x dash and change in t dash. Okay, so I can make comparison between u dash and u here by looking at how these formulas for x dash and t dash behaves. So I already have x dash in terms of x previously given by this, and t dash given by one below. Okay, so what one does in this particular case, then in order for me to get v, so I just divide by dt here. So I get dx dt, which is actually your u, and then dt divided by dt will just give you v there. And over here again the same thing, you get 1 there, and dx dt here will give you a factor of v, multiply that v, you get a v squared. Okay, so for this addition of velocities, so is given by well, I mean, this is u dash in terms of u first, but you really want to see what u is in terms of u dash. Okay, so you invert this, okay, formula, and you get this new velocity addition formula. Formula, or sometimes it's called the relativistic addition formula of velocities. Okay, so you can see that, okay, given that in O dash the object is actually moving velocity U dash, and then I have the frame itself is moving with velocity V, you almost have the same what you call formula like the case of the Newtonian mechanics, but you are modified by this factor here. Oh, sorry. Earlier I mentioned about this is actually U. Sorry, I've forgotten. Dx dt here is U. So you see that you have this factor of U dash times V over C squared. Okay, so it's been modified. If, for example, no, both this quantity is very small compared to C, which is most of the time it is, you'll find that you get back to your Newtonian mechanics. Okay. So now how does this actually relate to some of the formulas that we have seen before is you can think of your, if you divide this equation by C, okay, and then essentially I have U over C here, U dash over C, V over C. I can rewrite U dash over C as tangent, hyperbolic tangent alpha 1, and V over C as tangent alpha 2. Okay? And what happens inside here is essentially is a hyperbolic tangent of these two angles. So in other words, your addition formula comes into these angles that define the so this one, for example, is like, if you think properly what it is, this, remember there's a body moving O dash frame, so that body will have its own frame, so this will give you the alpha 1, and then the frame of O dash itself will have another velocity and will have another angle here, so you have these two angles being added up together. Okay, so in other words, it's, if you're looking for some kind of simplicity in this relativistic addition formula for velocities, it's actually inside your hyperbolic tangent. Okay. Here again, most of the time you can actually check that what you see is just no, almost equal to the case of the Newtonian mechanics. Yeah. Okay. And the other thing is perhaps one of the things that one has is that your hyperbolic tangent is less than 1, okay, because hyperbolic tangent is just what, ex minus e minus x divided by ex plus e minus x. So this is always greater than that. Okay, so you get always u over c less than 1. So in other words, u will be always less than c. So in other words, always you find that c will be a limiting speed in some sense. And if you try to put, for example, the body has speed of light, for example, a light inside the moving frame, okay? So a photon inside a moving frame will have velocity c, or a speed c, and according to the formula, if it's taken literally like the Newtonian case, then that photon in that moving frame will have speed greater than c. That is in the context of Newtonian mechanics. But that doesn't happen, because if you do that in the relativistic sense, you still have this modification factor here, and that will come out to be again to be equal to c. So your photon in the moving frame, will not move faster than speed of light. Okay. Now, one of the things one can think about is, okay, that is, I'm assuming that my object is just moving in the x direction, but I can think of a object in moving in all x, y, and z direction, and then you might want to ask, okay, what would be the changes of all these velocity components? Well, again, one does the same thing, but now when it comes to comparing the y component, you see that there's no changes with respect to this dt over here. Okay, and then essentially you'll get a slightly different addition formula for the case of the orthogonal components, which is given by here. Okay. So, okay, now I'll let you do the algebra itself, and then again, all this algebra always carries some physical meaning, so you need to sort of reframe your formulas physically so that you can understand the physics. Okay. Are there any question at this stage? I'm pretty sure this might not be the thing that you've seen in modern physics. Did you learn modern physics in this way or differently? Anyone?
We don't do all this, it's just plug and chug.
Pardon?
We don't do all this in modern physics, it's just using the formula directly.
So do you do addition of velocities?
We stop at time dilation and length contraction.
Okay. So in other words, this will be probably be new to you, okay, in some sense. Okay. So I'm getting to the last section of this lecture, and I probably want to stop at this section rather than continue, because the next section will be a completely new thing. So now what we wanted to do is to consider a possibility of what you see in stars, for example, is that you have this idea of aberration of light. Okay. So what one tries to do in this particular case is to consider your motion of light rather in one direction. You consider it to be moving in some plane. So this again is a simplified version, because you can have all components to be non-zero here, but no, we just stick to this xy plane. So you have a non-zero component here, a non-zero component here, and similarly for the case of your what you call your O dash frame, there will be a non-zero component here and non-zero component here. Okay. Now one could what you call rewrite these components in terms of their speed. Okay, so here's the components. The x component is just the speed times cos theta, and the y component is the speed times sine theta. Okay, and similarly for the O dash frame, then you have the speed u dash times cos theta dash, and then the speed u dash times sine theta dash. Okay, so what's going to happen is that, okay, I have now components related to the speed, right? And also the other thing that one has is the angle. Okay, the angle are also going to be different. Okay, so I have my relativistic addition formula of velocities earlier. So again, I'm still considering your O dash frame is moving in the x direction. Okay, velocity v. Okay, so the x component, for example, are going to be related by the relativistic addition formula by this amount, okay? And the y component will have slightly different, okay? We'll just have this modification there. And then what's going to happen is I can now make a comparison between these two formulas. If I divide say this formula with that formula, I'm going to get rid of this particular u. So I'll be getting your tangent theta written in terms of this angle in the O dash plane. Okay. So that is one thing that we can have. So we will see how the angles of the components are actually related in this sense. But let's make it a bit more specialized. In this case, you let your u dash to be equals to the speed of light. That means it's a photon. Okay. Then I will have this to be c, and then this also to be c here. And then you can start making a rearrangement of the formulas, and then you get this particular formula for the tangent theta here. So this tangent theta is now related to this tangent theta. Okay. So what one can now do is, okay, I'm going to make some approximation here. So I let v over c much less than 1. Okay. Then this 1 over 1 plus v over c secant theta dash, I can approximate it by, just like 1 plus x, where x is small, can be written as 1 minus x. Okay. So I can use that approximation to relate between tangent theta and tangent theta dash over here. Okay. And further, we assume also if the angles are quite small, the deviation of the angles are quite small, then I can set, for example, theta equals to theta dash by a small amount. Okay, so in other words, over here, your tangent theta is tangent theta plus delta theta dash, delta theta, then I can do an approximation of your tangent theta by a Taylor series. Okay, so I get tangent theta dash plus delta theta secant squared theta dash. This is essentially your derivative of your tangent theta. Okay, and then I'll be able to see directly how your tangent theta deviates. And if we take theta itself to be very small, do I need that? Let me figure out. So I will get hang on a minute. Yeah, I probably need that. So in other words, I can approximate this by, when tangent x do I need that? Probably I don't need that. So I'll do that delta theta here, and then our secant squared theta. I can't remember how I derived this formula. Okay, check this. But in other words, one can actually find your delta theta here from this expression above. Oh, silly me. Okay, it's going to be this expression. Okay, and then you have that expression that will be tangent theta dash plus delta theta secant squared theta dash equals to tangent theta dash 1 minus v on c secant squared secant theta dash. And I hope on arrangement, so you can so I have that on tangent theta dash. Then cancel that, sorry. Oh, okay, I mean, I'm not going to do this, I suppose, here, but it's that expression compared with that expression, and then you should be able to simplify that. If you have any problem with that, we can go through again. So in other words, what we have is that tangent theta dash over secant theta dash, and remember what is tangent is one sine over cos, and then this will be what, 1 over cos. So your cos will actually cancel out, and that gives you a sine theta. Okay, and this formula is useful in the sense that one can actually estimate amount of what we call aberration of light due to the motion of observer. So imagine you on the earth actually moving certain kind of speed due to the rotation of the earth. Okay, and then you have the fixed stars. Okay, so you look at the light from the stars, so there will be some aberration caused by our motion in space. Okay, and that aberration is given by this delta theta thing. So one of the things that people do is to assume that your theta dash is going to be pi over 2. So the light is actually initially directed perpendicular to the frame of the earth, and then you see due to the motion of the earth in space, there will be some aberration caused by that motion, and that is given by delta theta, and essentially that is going to be approximated by v over c. Okay, and that v over c, that v is the moving frame of the earth, and you can take the velocity to be approximated by the average speed of the earth, and the amount of aberration that you actually will see is about 20 arc seconds. So this, no, I'm not an experimentalist myself, but they have actually seen this kind of aberration inside observations. Okay, so that more or less the kind of Lorentz kinematics that we can actually get from all this idea of a moving frame. Okay, so this again, I believe you have not seen it before, this idea of aberration of light. This is printed in some books quite detailed, so you can have a look at the books if you want to. Okay, so let me see what else. I think I'll stop earlier today if that's okay. Are there any questions at the moment? Twin paradox or anything? No one? Let me get the attendance first before I forget. Now, if there are questions, again, I promised that I should give you some assignment, but I've not actually done that. Okay, hopefully either I give it to you during the weekend or early next week. Okay, this is week 3, right? Okay, so I should give you one assignment before the first test. Yeah. I'm sorry. What effect you are asking on? Time dilation, is it? What's the difference? Uh, well, put it this way. I mean, it's part of the same thing because it's coming from the boost transformation, but there are two different phenomena in some sense because one is you just concentrate on the time coordinates, okay, and the other one is actually you concentrate on your spatial coordinates. As you can see, when you try to compare both uh, things together, you have, for example, okay, as I mentioned, when you do the length contraction thing, what one does is actually you are looking at when you measure the length of a rod, it's actually done simultaneously only in one frame. Okay, the other frame is not going to be simultaneous. Okay, so there is a problem in a sense to make the direct comparison in that sense because in the O dash frame, for example, there will be some addition of these partial components. Okay, but one can actually use this idea of the invariance to see how to make comparison between what O dash measure and what O is measuring. So one can concentrate on that, for example, just the length, and then you find that okay, in this case you get the idea of a moving ruler is actually contracts. Okay, but there is these both effects are actually playing at the same time. See, because when you do the time dilation thing as well, there is some spatial components taking place as well, the transformation. But because we want to make the comparison between uh, time components only or spatial components only, without taking into the fact of that those are going to be modified by the respective spatial or temporal components. Okay, I'm not sure whether it makes sense or not. No, you just go back to the case of the length contraction. We had to make the assumption that okay, let me go back here. In order for me to make comparison between the two lengths, okay, what did I do? Was it? Okay. What did I do in this particular case? I had to make the assumption inside this this is the right transformation, the full transformation, and the full transformation will actually have this contribution. But since I want to have this formula, which is actually your length as measured by O dash, I made the assumption that okay, let's make that comparison directly, okay, by saying your T1 dash is going to be equals to T2 dash. In real fact, that effect is still there, okay, and similar for the case of the time dilation. Okay, I hope that. I mean, it's a little bit confusing because you're trying to measure. As you see, the simultaneity is not there in both frames, so you have to somehow make some further assumption to do this particular comparison. Is that good enough or it confuses you further? To me, one of the things that I do as a student in those days when the usually when you think of this physical thing, I always revert back to the formula. What does the formula say? Okay, because the formula is more direct. When you put in words, you have some extra connotations that comes with it. Okay, does that answer your query or not? Okay. Uh, is there a message? Timothy, do you want to say something? I'm not sure what that is. That was 10:32. I'm not quite sure what you're referring to here. Oh, okay. So I hope in some way you have to digest the notes quite well before before being able to look into some of the problems that comes with it. So my suggestion is maybe for a particular section which is confusing. No, it's not even confusing only for you. Sometimes even the experts will have confusion when it comes to saying things in words. Okay, it gets muddled up quite easily because you have frames that no, you have to talk simultaneously about both frames. Okay, are there any immediate questions before we stop? Yes or no? I guess no. Or you can give me a signal saying that I can stop now. Okay, great. All right. So I'll stop for now. If there are questions, you can put in the WhatsApp group. If there's some question of certain urgency that you need to have answered. Okay, I'll stop. So thank you, everyone. Bye. Bye.